Good day, dear learner. I welcome you in this new session in which I'll be talking about normal probability curve. So this particular session will be dealing with how we are supposed to define normal probability curve. The second part of the session will deal with the concept of symmetry in the normal curve and how it differs from skewed distribution. And lastly, you will be able to compare and contrast positively skewed, negatively skewed, and normal curve. Okay, so let's get started. So, what is a normal curve? So, normal distribution, which is often referred to as Gaussian distribution as well. It is very fundamental if you're studying statistics or if you're studying finance. Reason being because the reason is because of its symmetry around the mean, which is forming a very peculiar characteristic that is the bell curve. Like you can see here, this is the bell shape. This is how the bell looks like, right? So it's a bell curve that is being followed. Now it shows that data values are distributed in a symmetrical bell-shaped pattern around the mean and average. So that means the center of this is where we will have the mean, which is also equal to the median, which is also equal to the mode. Okay. Now the shape of the curve helps in understanding how values are spread out or how likely they are certain, you can say, extraordinary values that are lying along the bell curve, right? So all normal distribution are symmetrical and they have a bell-shaped density curves with a single peak. This is the single peak. So in any normal distribution, two quantities have to be specified. First, we should know the mean M and where the peak of the density occurs, right here. This is the point, right? And the standard deviation, that is S, which indicates the spread or the girth of the bell curve. Now, like I was saying, like this is a very common, you can say it is fundamental to statistic and often used in financial aspects as well, because we have to understand that, for, for example, in a stock market, like there are a lot of risk pattern there, right? So, but the average performance will always reside at a certain area. Okay, so the certain area will be somewhere here, but there will be some circumstances in which there will be extreme gains or there will be some extreme losses as well. So we see that this, though it is very rare, but it is a possibility as well. So the same way in statistic, when we follow the normal probability curve, this means that there may be some extreme values which might occur with a very low probability as well. Now let's have a look at this bell curve. Now this image represents the bell curve, which is, you can see the shape. This is the shape of a bell, right? Now the horizontal axis shows the range of the performance. This is the range of the performance here, the horizontal, from poor to excellent. So here it would be poor and this would be excellent. And the vertical axis actually represents the number of people. So here is the number of people. Number of people or number of students, right? Who have been basically judged according to their performance. So now what do you mean? If there is in this bell curve, this is the part where majority of them are meeting the expectation, right? So the majority of the students, they perform at an average or expected level. Now this forms the peak of the curve. 10% below that, this is the part where a small group which are very far below expectation, indicating there is a need for improvement. Then there was below expectation, another category, it is 15%, which shows they're slightly better, but still they're underperforming and they might require some training or mentoring in order to improve. Then after the 50%, we have above expectation, right? Another 15% here, which means these individuals, they're exceeding the performance standard and they show strong competence as well. And the excellent performance, that is 10%, which is also in a rare, they're top achievers who consistently, they have performed exceptionally well, and they represent the high performing edge of the group. Now, by looking at the bell curve, now just see how that you can, the educator or any teacher, they can visualize the performance distribution trend. Which are the students in which they need to really work, provide remedial measures, which are the gifted students, and which are the average students. So it gives you a bird eye view regarding how the students have performed. So now coming to the definitions, there are different definitions given by famous statisticians. So first definition is given by Garrett. He says that NPC, that is the short form of normal probability curve, it is a symmetrical, bell-shaped, symmetrical, bell-shaped curve, which represents the distribution of a continuous variable in such a way that mean, median, mode, they all coincide. And most of the observation, they cluster around the mean. Another definition given by Guilford, he also says that NPC is a theoretical curve so defined that its mean, median, mode are identical and the frequencies are symmetrical distributed about them. Now coming to empirical rule formula. The empirical rule formula, which is also known as 3 sigma rule and which is also known as 68, 95, 97.7, 99.7 rule. Now this describes the data, how it is being distributed in the normal bell-shaped distribution. Now according to this rule, the empirical rule, 68%, I'm just rounding off to 68, basically it is 68.27. 68% of the data lies between one, this is the first standard deviation. So this is where 68% of the data is lying, the average that we just saw in the previous slide, right? Then 95% is lying at the 2 deviation, 2 standard deviation, right? 95%. And 99% are lying at the 3 standard deviation of the mean. So the empirical rule, it basically allows the researcher to calculate the probability of randomly, obtaining a score from a normal distribution. Now in this slide, now this is just like what I have just told you, how 68% of the data is falling under the scores between -1 to +1 standard deviation from the mean. Now, for example, if the mean in this case scored by the student is 70 and standard deviation SD is 10, right? So, according to the empirical formula, 68% would score between, so you have 70 plus and minus 10. So we'll be having range between 60 to 80. So that means 8% of the students will score between 60 to 80. 60 to 80 score will be scored by 68% of the students. Likewise, you can calculate the similarly from 70 to plus minus 20. You can also calculate 70 plus minus for 20 and 30, right? So you will get accordingly. So, and that will show you how 95% is between this particular scores that will be ranging around, you can say 50 to 90, right? And this would be around 40 to 100. 99% of the students will be lying under 40 to 100 scores. So that's also, you can see now NPC actually also helps you to calculate the number of students who scored in that particular range if you know the mean and standard deviation. Now moving forward, now NPC and skewness, which refers to the degree of symmetry. But we know that normal curve is perfectly symmetrical curve. Perfectly symmetrical, that means it is neither skewed and the values of mean, median, mode are not different, they're exactly the same, and you can divide the curve, the bell-shaped curve into two. So if you want to fold it, you can fold it and you can see it's the mirror image, right? For the left side is the mirror image of the right side. So zero skewness, what does it mean? That it is perfectly symmetrical. The left side are the mirror image of each other, in which mean, median, mode are the same. The left tail is equal to the right tail in length and in shape. So there is no pull towards one side. It is perfectly balanced. This is known as zero skewness. Now coming to the part in which we'll be looking to negatively skewed distribution. Now what does negatively skewed distribution mean? So this means that here the mean, it is less than the median, which is less than the mode. And because there are few low scorers, so they pull the mean towards the left side. And it becomes smaller than the median, and then it becomes smaller than the mode as well. So the tail towards the left, that is why it is known as negative direction. The long tail on the left side represents the presence of very low or extreme values, and the peak is towards the right. So the peak is towards the right. So most of the data cluster towards the higher values here, indicating generally there is a very strong performance or higher scores. In the education setting, suppose a teacher gives a very easy test. So the most students have scored very high, 80 to 100 marks, but a very few students have scored between 20 to 40 marks. So here the majority of the data point scores will lie on the right side. And this is what we see in the graph. It is lying on the right side and the tail is extended towards the left side, making it negatively skewed. So why is it negatively skewed? Because it could be that the test or the task was comparatively very easy. So participants, they performed extremely well. There's an upper limit. This is also known as ceiling effect, which is beyond which values cannot go more than 100. Maximum value is 100. For example, the highest score is 100. So the maximum test score would be 100. So data naturally cluster towards the higher values, such as it could be, if you're running a satisfaction program, you're taking a feedback from any customers, or you're taking a very easy test. This is exactly how you'll find a negatively skewed distribution. Now let's look at the positively skewed distribution. So now the positively skewed distribution, of course, unlike the negatively skewed distribution, it is the opposite. So here the mean would be greater, here the mean would be greater than the median, and then the mode will be the least. Now why is it happening so? Because a very few high values are or high values, or which are the outliers also, they pull the mean towards the right here, making it greater than the median and mode, right? And the long tail on the right side represent extremely high values in the data set. So most points, they cluster at the lower values, which is a gradual decline towards the higher values. So we see that more of them are clustering towards the mode. You can see that is the low values. If you look at the horizontal axis, it is from low to high. So it is clustering towards the low values. So why is it happening so? Because the test could be comparatively very hard for the participants. So they scored very low in their particular test. And it sometimes happens that because just like we saw in the negatively skewed distribution, it was a ceiling effect. So positively skewed distribution, it has a floor effect, right? So when we're talking about the floor effect, we are basically talking about the task is too difficult and where the data is bounded at the lower end. So that means the test score cannot go below 0. There in ceiling effect, it cannot go above 100. Here it cannot go below 0. So a few extremely high values pull the mean upwards. So of course, unequal opportunities of resources or very tough tasks can also cause this kind of a skewness. Now let us look at some of the conclusions regarding the NPC. So if the values of mean, median, mode are the same in any distribution, then the skewness will not occur. It does not exist. So the larger the difference in these values, the larger the skewness. Number one. Number two, if the sum of the frequency is equal on both the side of the mode, then skewness does not exist. This is another assumption. So if the sums of frequency on the right side is equal to left side of the mode, then the skewness does not exist. Now, if the distance of the first quartile and the third quartile are the same from the median, and median is what? The second quartile. So if the distance from the first quartile to the second quartile are same as from the third quartile and the second quartile, that means that there is no skewness in the NPC. The same with deciles. Now, if you compare with first and ninth or first with 99th, they are at equal distance from the median, then there is no asymmetry. Now, if the sums of positive and negative deviation obtained from the mean, median or mode are equal, so there is no asymmetry. Then if the graph of data becomes a normal curve, then and if it is folded in the middle, it overlaps one another, which again shows that there is no asymmetry. So if you look at the formula of the skewness, so this is how you calculate the formula, where n is the number of data point, I is each data point. Here you can see here, this is the mean of the data and this is the standard deviations. So if you look at the skew value, if it is positively skewed, it will be less than 0, right? And if it is negatively skewed, it will be, it means that, sorry. If the skewness value is 0, that means mean, median, mode, they're equal. It is normally distributed. If positively skewed is greater than 0, then it is right skewed, right? And if it is negatively skewed, that means it is less than 0, then it will be left skewed. Now coming to kurtosis. Now let's look into kurtosis, which is a statistical measure to describe a characteristic of a data set. So it generally takes the form of a bell when normally distributed data is plotted on the graph. So the plotted data that are farthest from the mean of the data usually forms the tail. The farthest form the tail, and of course, which will be clustered around the mean in will form the peak. So kurtosis indicate how much data resides in the tails. So kurtosis, another word, it describes the fatness, you can say, the thickness of the tail found in probability distributions. So there are three types of kurtosis categories: mesokurtic, normal; platykurtic, that is less than normal; leptokurtic, that is more than normal. So how does kurtosis actually work? So kurtosis measures the weight of the distribution tail relative to its center mean. It helps in the identifying the presence of extreme values or outliers. Now, in a normal distribution, data lies within plus and minus 3 standard deviation of the mean, right? So with high kurtosis, that means the tail, it extends further, indicating that there are more extreme values. Kurtosis is often mistaken for peakedness. You know, the peak of the normal probability curve is usually confused with that, but it's actually measures the tailness, the shape and weight of the tail in relation to its overall distribution. So distribution can be sharply peaked with low kurtosis or have a flatter peak with high kurtosis, depending on how the data is spread in the tails. So high kurtosis means the data is in the tail, suggesting that higher likelihood of the outliers, while low kurtosis means there are lighter tails. That means there are very few extreme deviations in that particular curve. Now I'm using the word outliers. What are outliers? Outliers are basically, you can say that they are the data points which are significantly different from the rest of the observation, or they're the values that are farthest away from the average or from the mean, or the general pattern. Or you can say the outliers is they deviate so remarkably that they may indicate variability, they may indicate error, or they may indicate some kind of a unique phenomena. That is why they're residing in the tail. They're not clustered around the mean. So leptokurtic, it indicates a positive axis kurtosis. That means this distribution shows heavy tail. Now you can see the tail width of the leptokurtic, and that shows that the kurtosis is greater than 3, and it has a sharper peak here, and but compared to the normal probability curve, but the tails are fatter. That means they're more extreme values or outliers. This indicates likelihood of rare extreme events. Now coming to mesokurtic. Mesokurtic is it is a moderate peak with the kurtosis is equal to 3. There are no extreme outliers, and the distribution is neither too peak nor too flat. And it shows basically a normal frequency of outliers, and not too many or not too few, and it basically represents a well-behaved symmetrical distribution. Platykurtic, on the other hand, it shows a negative axis kurtosis, which shows it indicates small outliers, which is less than 3. It has a more flatter peak because the tail here is becoming thinner, which shows a very few extreme values or outliers and less likelihood of rare extreme events. So this is the formula for measuring kurtosis, and in which it is self-explanatory that n means number of observation, xi here means each data point, this is the mean and this is the standard deviation. The more easy way in which you can also calculate kurtosis is through percentile. Now here you have to understand, if kurtosis is equal to 0, that means it's normal distribution, mesokurtic. If it is greater than 0, that means heavier tail and a sharper peak than normal, leptokurtic. And if it is less than 0, that means the distribution has a lighter tail and a flatter peak than normal, that is platykurtic. So if you look at the kurtosis, this is another way, just like I said, but through percentiles, where quartile division is divided by percentile, 90th percentile minus the 10th percentile. So here, if you get the value kurtosis of 0.263, it is normal curve. And if it is less than 0.263, it is leptokurtic distribution. And if the value is more than 0.263, it is platykurtic. Now coming to skewness and kurtosis, this is a tabular form in which skewness is being differentiated by kurtosis. Now if you pause the video and read the points, you will understand how the skewness is basically talking about the shape and variation on either side of the central value, right? That is, it's talking about mean. It is indicating how far the distribution is differing from the mean. The measure of skewness is studied to the extent, the measure of skewness studies the extent to which deviation clusters is and are above the average. And in an asymmetrical distribution, the deviation below or above an average is not equal. This is where the whole concept is concentrated towards the mean and how it is being distributed. But on the other hand, kurtosis, it is the frequency of distribution at the central value. It indicates the concentration of item at the central part of the distribution, and basically it is also indicating where the concentrations are and how the outliers are basically in the tail region also. Then moving forward, why is it so important to study NPC or normal probability curve? So NPC is basically closely represents the real world variables. Now, if you look into education, if you look into the exam scores also, we can easily, through looking at NPC, we can see the average marks, the students who scored the higher marks, how the higher end, and how they scored, the students who scored below average, just like in the previous slide that I showed you. The same way, if you want to measure human height, if you want to take the IQ scores of the students, all that can be done by following the NPC, normal probability curve. So the average IQ is 100, so the most people will fall between 85 to 115. Very few people will be 113 above, and low IQ would be 70. So IQ distribution follows a normal distribution as well. Now, on the basis of hypothesis testing also. So if you look at the hypothesis testing in especially in Z-score and T-score, we compare the observed sample result to what is expected under a null hypothesis. So the NPC basically helps to determine the critical values and confidence levels and p-values, that is the significance level. If the test statistic falls in the critical range, that is the tails of the NPC, we reject the null hypothesis. If it falls in the central region, then we fail to reject the null hypothesis. We basically accept the null hypothesis. Like, for example, a new drug is being tested. So the NPC will help assess whether the difference in the recovery times between the treated and the untreated group is statistically significant or just due to chance. So NPC, you can say it's like a map in hypothesis testing. It helps identifying whether the observed result is normal, likely, or extreme, that is unlikely, if the null hypothesis were true. The next importance is the predictability and the empirical formula. So remember the empirical formula I talked about as 68, 95, 99.7. So how 68% of the data lies in first standard deviation, 95 lies in within the second standard deviation, 99.7 lies within the third standard deviation. So this predictability helps in estimating probability. It helps in estimating the risk and the outliers also. So it shows how likely a certain value is to occur. For example, in a quality control, if the product measurement falls outside the third standard deviation, then it can be flagged as a defective or unusual item. Now, coming to the fourth importance is identifying the skewness and the outliers. So when data does not follow the normal probability curve, it may be skewed or containing outliers, right? So even in medical research, a skewed distribution of blood pressure reading would show what? That it indicates that there is a health issue in that specific group. Then also it is being widely used in the research and quality control. We find that even in research, a researcher, for example, is studying a new reading program and comparing the student's test result. So if it follows a normal probability distribution, the researcher can use t-test, right? And they can determine whether the improvement is statistically significant or not. So the NPC basically helps visualize how much of the improvement is due to the program and how much might be because of chance or random variation. Similarly, in quality control, for example, a chocolate factory is producing chocolate bars of 50 grams each. So if it is the daily samples are tested and they're plotted in a chart, in the form of chart, and if it shows bell-shaped curve, so most of the bars will be 49.5 grams to 50.5 grams. But if there is some outliers like 49 grams to 55 grams, so those data points, those will lie in the tail of the NPC, signaling that that production is going out of control and it needs correction. So to conclude, NPC is one of the most significant concepts in statistics, forming the foundation of understanding how the data is distribution and how it is varying, what is the variability. And it represents an idealized pattern in which most of the observation they cluster around the mean and a very few of them they move out in the form of outliers in the tail. So if you're studying the properties of skewness and kurtosis, learners or statisticians, they can identify deviation from normality and interpret the underlying characteristic of data more accurately. So in essence, we can see that NPC, it enhances our understanding of randomness and order in natural and social phenomena. So its application in education, psychology, research, industry makes it an indispensable concept for students and professionals aiming to analyze and interpret data scientifically and meaningfully. With this, I've come to the end of my today's lecture. These are the references that you can refer to and study more in detail regarding NPC. So thank you all for your patience listening. I'll be seeing you again with another topic, interesting topic related to NPC. So see you then. Have a good day. Bye bye.